In this video, we'll be learning how to build Jovian planets. That is, the large gaseous planets like Jupiter, Saturn, Uranus, and Neptune. Now, whereas there are a number of ways to categorize Jovian planets, the simplest and arguably the most useful is by their location within the planetary system, as their distance from their parent star strongly influences their properties. This gives us four types of Jovian planets, which we're going to call fire giants, steam giants, gas giants, and ice giants. Fire giants, which are more commonly referred to as hot Jupiters, lie extremely close to their parent star and, as a result, are extremely hot. They have orbital periods on the order of a few days, and due to their very limited hill radius, they are not likely to have major moons. If you're not familiar with a hill radius, don't worry about it. I'll be covering it in the next video. Steam giants are found a bit farther away in the inner region of a planetary system, which includes the habitable zone. They have orbital periods on the order of several months to a couple of years and are likely to have a few major moons with predominantly rocky compositions. Gas giants lie in the middle region of a planetary system, with the solar system planets Jupiter and Saturn being archetypal examples. They have orbital periods measured in decades and are likely to have several major moons comprised of rock and ices, some of which may even support subsurface oceans of liquid water. Finally, ice giants are found in the outer region of a planetary system and are usually on the smaller side in terms of mass. They have orbital periods ranging between several decades to a few centuries and are likely to have major moons comprised predominantly of icy materials. The solar system planets Uranus and Neptune are examples of this type of planet. I'm going to make my own Jovian planet, a gas giant that lies about halfway into the middle region of the planetary system. So I'm going to record its semi-major axis, or average orbital distance, as 6.3108 AU. Where you place your Jovian planet will likewise depend on the type you've chosen. Fire giants should be placed less than 0.1 AU from their star. Gas giants should be between 4 and 14 AU, and ice giants should be beyond 14 AU. Steam giants should be placed at a distance between 0.1 and 4.0 AU. But if it is to be within the habitable zone, then you should follow the instructions in my previous video to calculate the appropriate distance based on the desired stellar flux. Link in the card and video description below. Also, all of the distances listed here are relative to a star of one solar mass, so you will need to multiply these numbers by your star's mass, in solar masses, to get the specific values for your system. The next parameter we should define is the planet's mass. Jovian planets have a very large mass range, which spans from approximately 0.025 Jupiter masses up to around 13 times the mass of Jupiter. About 4.8 times 10 to the 25 to 2.5 times 10 to the 28 kilograms. The mass you choose can be anything within this range, but it's important to remember that the mass of the planetary system is proportional to the mass of the parent star. As I pointed out previously in this series, the lower the mass of the star, the smaller the likelihood of it containing a large Jovian planet. So for optimal plausibility, I would suggest limiting the total amount of mass in your planetary system to something less than half of 1% of your star's mass. That's a multiplication of 0.005 times the mass of your star. If that seems low to you, it might be helpful to note that that is well over twice the amount of mass contained in our solar planetary system. So before I set the mass of my Jovian planet, I'm going to estimate the total mass of my planetary system by multiplying my star's mass of 1.8023 times 10 to the 30 kilograms by 0.002374, which is just some arbitrary number below 0.005. That gives me a total mass of 4.2787 times 10 to the 27 kilograms. That's about 2¼ Jupiter masses. Since I'm likely going to add a few gas giants to the middle and outer region of my system, I'm going to set the mass of my largest Jovian planet to 1.2814 Jupiter masses. I'm going to add that value to my sap sheet and then multiply the number by the mass of Jupiter to get my planet's mass in kilograms. So that's 1.2814 times 1.8982076 times 10 to the 27 kilograms. I will then record this to my SAP sheet as 1.4324 times 10 to the 27 kilograms. Next, we will define the radius of our Jovian planet. This is a parameter that is very easy to get wrong, as Jovian planets do not necessarily possess a size that is proportional to their mass, as terrestrial planets do. To help us find a plausible radius for our planet, we're going to make use of this graph, which is derived from data of several dozen Jovian exoplanets for which we have mass and radius measurements. The mass of the planet is given along the horizontal axis in Jupiter masses, and the size is given in Jupiter radii on the vertical axis. The orange lines represent the upper and lower size limits for a given mass, and the gray line represents the median value. Most Jovian planets are going to fall on or near the median line, but there are two factors that can cause them to move above or below the line: composition and temperature. The composition of a Jovian planet is predominantly hydrogen and helium, but invariably some fraction of their mass will be elements heavier than this. Astrophysicists call this the planet's metallicity, because astrophysicists define metals differently than chemists do. The higher a Jovian planet's metallicity is, the smaller the planet will be. This is why the low-mass planets on the left side of the graph can get so small. Their low mass means that a higher percentage of their composition can potentially be denser materials, while this isn't the case with the high-mass planets on the right side of the graph. There aren't enough metals present in a protoplanetary disk to form high-mass Jovian planets with a high metallicity. Temperature works opposite of composition. The higher the temperature of a Jovian planet, the more its atmosphere will want to expand, and the larger the planet will be. Due to the comparatively weak gravity of low-mass Jovian planets, their atmospheres can expand out considerably. This is what leads to the so-called puffy planets. But the gravity of high-mass Jovian planets is so strong that their atmospheres are compressed and kept far more constrained. Due to these two factors, it is entirely possible to have a planet that is only a quarter the mass of Jupiter, but 50% larger in radius, or a planet that is 3 times the mass of Jupiter, but 10% smaller. My planet is about 28% more massive than Jupiter, so I'm going to place its radius close to the median value, say 1.3625 Jupiter radii. I'll record this value on my SAP sheet and then multiply it by Jupiter's nominal volumetric radius of 69,911,308 to get my planet's radius in meters. When building other types of planets, we usually use these determined mass and radius values to calculate the planet's surface gravity and escape velocity. But when it comes to Jovian planets, both of these parameters are meaningless. Jovian planets don't possess a surface to measure gravity from, and measuring it from the top of the upper atmosphere is absolutely pointless. But if you want a parameter that makes some reference to the planet's gravity, I would recommend calculating its standard gravitational parameter, commonly referred to as its GM. This is just the planet's mass multiplied by the gravitational constant, and will be useful to have when we later calculate the orbital parameters of its moons and rings. So on the calculator, I'll enter my planet's mass, in parentheses, and then multiply by the gravitational constant, also in parentheses. Pressing equals gives us our GM value in cubic meters per square second. The only remaining geophysical parameter that I classify as critical is the planet's mean density, which is given by this equation and equal to 3 times the mass of the planet divided by 4 pi times the planet's radius cubed. So in the calculator, I'm going to start by opening parentheses and entering 3, multiply, open another parentheses, and put in the planet's mass in kilograms. Then close both parentheses, divide, open another parentheses and enter 4 pi times the planet's radius in meters raised to the 3rd power. Then close the parentheses. Your equation should look something like this. There are a number of important and optional parameters left that we can calculate for our Jovian planets, but since I have covered them in previous videos, I won't go back over them in detail here. Instead, I will place links to those videos in the description below, along with any special instructions needed to adapt the techniques for Jovian planets.